How fast is the universe expanding right now? It sounds like a simple question, but in modern cosmology, it has turned into one of the field's biggest arguments. The dispute is known as the Hubble tension, and at its core is a clash between two very precise answers for the present-day expansion rate, h0 or h0. h0 is usually given in kilometers per second per megaparsec. In plain language, it tells us how much faster galaxies appear to recede for each extra megaparsec of distance. A higher h0 means the universe is expanding faster today. A lower h0 means it is expanding more slowly. Why does that matter? Because h0 is not some technical side number. It affects our estimates of cosmic distances, the age of the universe, the scale of structures, and the whole story of how the cosmos evolved. If we are misunderstanding h0, the problem may not be limited to one awkward measurement. It could point to trouble in the broader cosmological picture. The tension is usually summarized like this. Methods tied to the nearby universe tend to give a value around 73. Methods tied to the early universe tend to give a value around 67. That gap may sound small, but at this level of precision, it is a serious mismatch. The best-known early universe route comes from the Planck mission, which mapped the cosmic microwave background, the ancient light left over from the early universe. Using those observations within the standard cosmological model, lambda CDM, Planck inferred h0 at about 67.4. But there is an important caution here. Planck did not directly measure today's expansion rate. It measured the early universe extremely well, and then inferred h0 through a model framework. So the Planck value is powerful, but model-dependent. On the late universe side, the most famous result comes from the JWST team. Their method uses a distance ladder, first calibrating distances with Cepheid variable stars, then using those calibrations for type Ia supernovae, and from there estimating h0. That program has found a value around 73.2. And the key point in the current debate is that the uncertainties have become small enough that the gap with the early universe inference is unlikely to be mere statistical noise. Still, this is not simply a duel between Planck and JWST. That is one of the most important complications. Nearby universe methods do not all agree perfectly with each other. Different local techniques, different calibrations, and different assumptions can produce different h0 values. So the tension is real, but the late universe side is not a single united block. One major criticism of the Cepheid route concerned crowding or blending. In images from the Hubble Space Telescope, some Cepheids sit in busy, stellar environments. If nearby stars contaminate the light, the measured brightness can be biased, and that can ripple through the distance ladder. This became one of the most serious, systematic concerns hanging over the higher h0 values. That is where a major 2024 result from the James Webb Space Telescope entered the story. With sharper infrared observations, JWST can better separate stars in crowded fields. The SH0ES interpretation of those data was that this specific blending concern is now very unlikely to explain the Hubble tension. In other words, one of the strongest objections to the Cepheid ladder was weakened significantly. But that does not mean the mystery is solved. The JWST result addressed one serious systematic. It did not rule out every local systematic. There can still be issues tied to calibrators, sample selection, photometry, supernova standardization, or galaxy motions. So it would be a mistake to treat the JWST blending result as a final victory for the high h0 camp. In fact, JWST also sharpened another important point. Local methods themselves show diversity. In 2024, Wendy Friedman's Chicago Carnegie program used JWST to test 3 nearby universe approaches. Cepheids again gave a value around 72. But the tip of the red giant branch method, usually called TRGB, came out closer to 70. Another route, JGB, also leaned lower. When combined, the result was just under 70. That matters because it suggests a pattern. Cepheid-based ladders tend to run higher, while TRGB and JGB tend to come in lower. So JWST did not definitively confirm one local answer and settle the debate. Instead, it pushed the argument toward calibration pathways, sample choices, and the overall robustness of each distance ladder. At this point, the question becomes larger than one number. Maybe the measurements are fighting because one or more techniques still hide small biases. Or maybe the model used to connect the early universe to the present is too simple. This is where DESI, the dark energy spectroscopic instrument becomes important. DESI does not directly measure H0. Instead, it maps cosmic expansion across billions of years by surveying the large-scale distribution of galaxies and quasars. Its significance is therefore not that it tells us H0 is definitely high or definitely low. Its significance is at the model level. DESI tests whether the expansion history assumed around H0 is actually right. In 2024, DESI results remained officially compatible with the standard lambda CDM model, but they also showed a slight preference for dark energy that may not be constant. Then, in 2025, those hints reportedly strengthened. The language here has to stay careful. These are hints, not proof. Depending on the exact dataset combination, the quoted significance varied from just under 3 sigma to above 4 sigma. If those hints survive, they would matter enormously. In the standard model, dark energy is treated as a cosmological constant, something fixed over time. If dark energy is not constant, then the lambda part of lambda CDM begins to weaken. And in that case, H0 may be less a single disputed number and more a symptom of a deeper mismatch in the assumed expansion history of the universe. But again, caution is essential. DESI has not directly shown that Aurora must be high or low. And even if dark energy varies, that does not automatically solve the tension. Some new models can help reduce the discrepancy, but others simply shift the problem somewhere else. Meanwhile, the case for the high side does not rest only on Cepheids. In 2025, several independent late-universe methods also leaned high, though often with larger uncertainties. TD Cosmo, using lensing time delays, gave a value around 72. A Type 2 supernova method gave about 74.9. A coma cluster distance route gave about 76.5. Taken together, these results make it harder to dismiss the high H0 side as nothing more than one Cepheid-specific mistake. Even so, the strongest counterargument remains serious. New physics may still be unnecessary. The discrepancy could come from multiple small systematics spread across local measurements rather than one dramatic flaw. Maybe calibrators are slightly off. Maybe selection effects matter more than expected. Maybe photometric choices, supernova standardization, or local galaxy motions, each nudge the answer in the same direction. And on the early universe side, the inferred Planck value could also shift if one of the model assumptions is wrong. There is also a more local explanation sometimes discussed, the void scenario. If we happen to live in a local underdensity, then the nearby expansion rate could appear higher than the cosmic average. Many cosmologists doubt that such a void can explain the full gap between roughly 67 and 73, but it is not ruled out entirely. So where does this leave us? The best supported picture right now is unsettled, but fairly clear in outline. The early universe inference still sits near 67. Many nearby universe methods still come out higher. JWST has reduced one major objection to Cepheid measurements without removing all doubts about local systematics. At the same time, other local methods do not fully agree with each other, which keeps the pressure on calibration and method choice. And DESI has opened the door to a more unsettling possibility, that the deeper issue may lie in the standard cosmological model itself, especially in how we describe dark energy and the universe's expansion history. So the Hubble tension remains unresolved. It could still turn out to be a web of careful but ordinary measurement problems. Or it could be an early sign that the model connecting the infant universe to the present day needs revision. Either way, this is not a minor bookkeeping dispute. It is a test of whether our most successful cosmic framework is complete. Subscribe, enable notifications, and suggest the next topic you want us to explore in the comments.